In today's lecture, I want to start off from where we left off, but discuss a couple of things that will be very necessary if we are to understand angular momentum addition. Okay. So remember that last time when we talked about the representation of the U matrix, right? So the finite rotation. So we found that the representation of the finite rotation, the matrix that represented rotation in the Hilbert space, had a very curious form, right? So it had the form of a block diagonal, which means that it was zero for the most part, but there was a 1 by 1 block that corresponds to the j equal to 0 part. There was a 2 by 2 block that corresponds to the j equals 1/2, the spin 1/2 block. And then there was a 3 by 3 block that corresponds to the j equal to 1 block, and so on and so forth. And no matter what matrices you're talking about, the j square, j1, j2, j3, whatever it is, they always followed this block diagonal form, which means that if you act it on any state, the jm states, then they do not mix states with different j values. Like this block diagonal form ensures that they do not mix states with different j values. And this came out naturally from the algebra of the angular momentum generators. So we gave a special name for this representation. This is called a direct sum representation. So there is two, of course, we have to expound a little bit about this. So today's lecture will be a short module in which we will discuss what these two kinds of new ways of constructing linear vector spaces are: the direct sum and direct product. Okay. And today it will be mostly, so there is, to understand angular momentum addition, of course, you have to understand how exactly one does it and the theory behind it, which we will develop carefully and explain what Klipsch-Gordon coefficients are and things like that. But at the practical level, one has to be able to understand how to write down the matrices, right? So the fundamental issue is this: when I talk about angular momentum addition, when I say that J equals L plus S, right? So I have to quantify what this means as a practical measure of solving problems. For example, I know that these angular momenta have generators. So suppose if I take L equals 1 and S equals half, I know that the matrix that represents, for example, L1, L2, L3 are 3 by 3 matrices. Right? And the matrices that describe rotation in the spin 1/2 case are 2 by 2 Pauli matrices, right? So now how do I construct a matrix for J? There is no sense in which I can add a 3 by 3 matrix with a 2 by 2 matrix. So I'll have to be able to understand how to do this addition as a practical measure. And we will develop two ways of constructing higher dimensional vector spaces from given vector spaces. Okay, so and we will use these concepts later when we talk about angular momentum addition. So today we will simply talk about direct sum and direct product and what this means. Okay, so I'll erase these things. And we will start with direct sum because we already introduced this concept earlier. So it makes sense to start with this. So direct sum. See, both direct sum and direct product of vector spaces are basically ways in which one can construct higher dimensional vector spaces from 2 or 3 or 4 or whatever it is given vector spaces. So let us take a simple case and then proceed to understand what this means. So the way I will do it is I will not go into a lot of mathematical details, but I will simply give you some examples to try and understand how such spaces are constructed. And hopefully we'll make a connection to the angular momentum as we go along. So what is this space? We will try to understand three different things. What is the space, which means what are the basis vectors, and how do the vectors look like, and how do the matrices look like in this space. So what is the space? So let us say that you are given two vector spaces. Let's start with two linear vector spaces. Okay. We'll call the first linear vector space V and the second linear vector space W. And we will say that the vector space V is n-dimensional and the vector space W is m-dimensional. Okay. Now, n doesn't have to be equal to m in general. So we are just starting with two different vector spaces. Okay. So on the vector space V, so again, these are just two copies of ordinary vector spaces that you know and love, right? There is nothing complicated about them to begin with. So let me define a set of basis vectors on V and W. So on V, let me say that my basis vectors are given by E1, E2, up to En. Okay, and these are basis vectors in the sense that if I do Ei dot Ej, I get delta Ij. It is 0 if I is not equal to j and they are normalized properly. Let me call the basis vectors on W some f's, some f1, f2, and there is m of them. Okay, and they are also proper basis vectors in the sense that fi dot fj is delta ij. Okay, now I will define n plus m basis vectors. I will define, and now I'm going to construct a new space by simply stacking one on top of the other. Okay, this is the simplest way in which I can construct a higher dimensional vector space. I take the basis vectors of the first vector, I take the vector space, I take the basis vectors of the second vector space, and I stack them on top of each other. So I will construct n plus m basis vectors, and this is called, this is basically E1, E2 up to En, comma, F1, F2 up to Fm. Okay, I'm just stacking them on top of each other. That's all. Okay, so the vector space that is spanned by these vector spaces, by these basis vectors, so vector space spanned by these basis vectors is denoted as the direct sum of the vector space V and vector space W. Again, don't worry about the specific notation. We have to understand what this practically means. Okay. In other words, we have to understand how the vectors in this direct sum vector space look like, and how do the matrices that act on these vectors look like in this direct sum vector space. Okay. So let us start with the vectors. So remember that in the vector space V and vector space W, I can simply define vectors. In the vector space V, my vectors are n-dimensional, and in the vector space W, my vectors are m-dimensional. By the way, I should mention that I'm talking about finite dimensional vector spaces here because I want to make a connection to angular momentum. But in quantum mechanics, we can also talk about infinite dimensional vector spaces and direct sum and direct product of those. A simple example would be given by momenta. I will mention this, but we don't usually use that language because it's a little cumbersome in that case. I'll explain what this means as we go along. So on the vector space V, how do my vectors look like? My vectors look like V can be written as sum over I equals 1 to n Vi Ei, right? And on my vector space W, my vectors W look like I equals 1 to m some Wi Fi. Okay. So let me actually make this more precise by writing down the vectors as column vectors, so it's actually easier for you to understand. So what I actually mean is that my E1, for example, is 1, 0, 0, 0, okay, with n entries total, right? And my E2 would be 0, 1, 0, 0, and E3 would be, as you can easily guess, 0, 0, 1, and so on and so forth, right? Similarly, for the space W, my F1 would again, I can represent this as 1 0 0 0, but in this case m entries. It's an m dimensional column vector, and so on and so forth. I can write f2 and f3 in such a fashion, and you can trivially verify that these guys satisfy the orthonormality properties that basis vectors are supposed to satisfy. Okay, all right. So so instead of writing my vector in this notation, I can also express my vectors as a column vector now, right? My v vector now can be written as a column vector with entries v1, v2, v3, vn. Similarly, my w vector can be written as w1, w2 up to wn. So far, so good. So there is nothing very complicated about this. Now the question is, how do these vectors look in the direct sum vector space? So how do these vectors look in the v plus w space? Okay. Well, the vector should not change to some other vector, but it should certainly be a higher dimensional vector because we are talking about a higher dimensional space. Okay, so you can easily guess that the form of the vector v in v plus m dimensional space should be very simply the v vector doesn't have any components along any of the f directions. So in the v plus w directional space, the vector v should simply be v1, v2 up to vn, and of course in the v plus m dimensional space, it's an n plus m dimensional space, so I should have an n plus m dimensional vector. So for all the f directions, I will simply put in zeros. Okay, so there is n components, n entries with v1, v2, v3 up to vn, and then I will fill in m zeros. Okay, so this is an n plus m dimensional vector. Okay, so how does my w vector look like in the n plus v plus w space? As you can easily guess, the w vector cannot have any components along any of the e directions, so I will put in n zeros. Okay, and then I will write the components along the f directions, which are m components. So there is n zeros and there is m. So this is also an n plus m dimensional vector, as it should be. Okay, the dimension of a vector in this vector space is the dimension of the vector space itself. Okay, so suppose if I add these two, I can also define what is called a direct sum of two non-zero vectors. Okay? The direct sum of two non-zero vectors, v plus w, is now given by v1, v2 up to vn, w1, w2 up to wn. Okay, you can understand this as the vectors being stacked on top of each other, basically. Okay, so there is n of these and m of this. So this is an n plus m, again, n plus m dimensional vector. Okay, simple enough. Any questions or any comments about this?
So can I go to the previous page?
Yes. Where, this one?
No, sir, previous one.
This one?
Yes, sir, yes, sir. Sir, here you are using EI and FI with same year entries like 100, 100. So can I change one of the entries because I might get confused that which one will be the EA. So like I wanted to say that for E1 I want to use 100 and for F1 I wanted to use 1 bar or 1 prime 00. Can I use that?
Of course you can. See, you can also use a completely different set of vectors. As I've repeatedly emphasized, there is nothing sacred about basis vectors. Okay, but whatever you do, the addition of the direct sum of these two vectors would be such that there is n v's on top and m w's on the bottom. Okay, now the actual values of w1, w2, w3 will, or the actual values v1, v2, v3 will depend on what basis vectors you've chosen. Okay,
Okay, sir.
so if I choose a different set of basis vectors, I will write this direct sum as some other v1 prime, v2 prime, vn prime, and w1 prime and wn prime. But it will still have the exact same form. N entries of v stack above m entries of w. Okay.
Okay, sir. Hmm.
The 100 is
Sir,
easy because it is the easiest basis vectors I can think of. Yes. Yes.
sir, I am a bit confused as to why cannot we have any components along F directions?
Because the way this vector space is constructed, I'm simply taking two vectors and stacking them on top of each other, right? So let us actually give you an example. So let us say that n equals 2 and m equals 3. This is an example that we will work out carefully, okay? So what do I mean? My V is now a two-dimensional vector space and my W is now a three-dimensional vector space. So on V, I have two basis vectors, 1, 0 and 0, 1. Okay, or as was pointed out, I can take any other set of basis vectors also. For example, I can also choose 1 over root 2, 1, 1 and 1 over root 2, 1 minus 1. That is completely up to me. I'm simply choosing 1, 0, 0, 1 because it's just easier for me to calculate things. On W, I have three basis vectors, for example, 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay, so far so good. So how does my V vector look like? My V vector is basically V1, V2, right? It is V1 times the first basis vector plus V2 times the second basis vector. My W looks like W1, W2, W3. It's W1 times the first basis vector F1, W2 times the second basis vector F2, and W3 times the third basis vector F3. Okay. Now, when I construct the composite space V plus W, I'm simply saying that this V plus W is such that I simply stack the vectors on top of each other. So how do my basis vectors look like in this space? Well, my basis vectors in the V plus W space look like this. So remember that I am simply stacking the vectors on top of each other. Now I should construct five-dimensional basis vectors, right? The way I will construct five-dimensional basis vectors is simply I will take these basis vectors. So let us say I'll take one E. Excuse me. 1, 0. Okay. And then I need to write down the corresponding basis vector for a five-dimensional space. So I will simply write 0, 0, 0. The second vector would be 0, 1. And along the three F directions, I will simply write 0, 0, 0. Okay. Now I need to convert the three basis vectors in the W space into the corresponding five-dimensional basis vectors. So I have 1, 0, 0 in the bottom. So I will simply stack two zeros on top. 0, 0, 1, 0, 0. Okay. Again, 0, 0, 0, 1, 0. And the last basis vector, as you can guess, would be 0, 0, 0, 0, 1. Okay, so these would be the five basis vectors in the composite space. And as you can easily verify, these are also orthonormal to each other. Okay, now remember that if I had started with a slightly different set of basis vectors, that is totally fine. My construction would have proceeded exactly the same way. So for example, if I had started with V with equal to 1 over root 2, 1, 1 and 1 over root 2, 1 minus 1, let us say, right? My first two vectors would be different. How would they look like? My first vector would be 1 over root 2, 1, 1, 0, 0, 0. And my second vector would be 1 over root 2, 1 minus 1, 0, 0, 0. Right? So regardless of what basis vectors you choose in each vector space, once you choose them, you simply stack them on top of each other to find the basis vectors in the higher dimensional vector space. In this case, it is a five-dimensional vector space. So in this case, V plus W is a five-dimensional linear vector space. Is this okay so far?
Yes, sir.
Okay. So now how does my vector, how do my V and W look like in this space? Okay. The way I would understand V in the V vector in this space is basically V has only two components, V1 and V2. So suppose if I talk about, see, let us say that So let us say that you are living in a two-dimensional vector, coordinate system, right? So let us say that you are living in two-dimensional coordinate system, and you have some vector A, which you write as AXI plus AYJ. Okay, right? Now, suppose you are solving some problem in some complicated mathematics or physics that demands that you work in a three-dimensional coordinate system and not a two-dimensional coordinate system. Now, you can always work in whatever dimensional coordinate system you want, but now you have to ask, how do I write this A vector in a three-dimensional vector space? Well, just because you are promoting your calculations in a three-dimensional vector space, the vector A doesn't magically generate one more component, right? So the way you would understand this vector A, the three-dimensional vector space, is AXI plus AYJ plus 0 times K. So you can understand this A vector in the three-dimensional vector space as having components AX along the X direction, AY along the Y direction, just like it was before, but has no components along the third direction. Okay, that is exactly what I'm doing. So I'm simply asking, how do my vectors V and W look like in this higher dimensional vector space? They cannot magically develop components along the additional directions that I'm simply pushing in. So the way I would understand V in this 5-dimensional vector space is having a component V1 along the E1 direction, V2 along the E2 direction, but no components along the other three directions. Similarly, the way we'll understand W in this higher dimensional vector space is having W1 along the F1 direction, W2 along the F2 direction, W3 along the F3 direction, but no components along the E1 and E2 direction. Okay. Now I can ask, how does an addition of these two vectors look like in the higher dimensional space? And this is called a direct sum of these two vectors. And the direct sum, of course, has components along all directions, because you're constructing it out of an addition of two vectors, one which has components in E1 and E2, and the other which has components in F1, F2, F3. So this composite vector will have components along all directions. Okay. So this is basically stacking the vectors on top of each other. Does this make sense or no?
Yes, sir, clear.
So this part by itself is easy. So the one thing that we have to understand is, how do the matrices look like? So there is a couple of ways one can understand a matrix. So in physics, the way we employ a matrix is by saying that matrix is usually an operator, right? So it takes a vector and then it gives you a new vector where A is a matrix. So for example, if I'm living in an n by n dimensional vector space, V is an n entry column vector and A is an n by n matrix, and V prime is also a new n entry column vector. So we simply think of this A as a matrix that operates on a vector to give you a new vector. So mathematically, what this means is that matrices are basically mappings. They are linear mappings from the vector space to the exact same vector space. Okay, so I can understand A. So what does this mean? This means that A is some kind of a black box, right? So if you feed one element of the vector space into this black box, you get another element of the same vector space from outside the black box, right? So this black box basically tells you a way to map the vector space into itself. So it gives you a vector. You input a vector in the vector space, it gives you another vector in the same vector space. So this is another way in which you can think of the matrix as a linear mapping from one vector space to the same one, because that is what we do in quantum mechanics. So in written it out completely, all I'm saying is that V1, V2, Vn, right, is mapped on to some A11, A12, A1n, A21, A2n, so on and so forth, AN1, ANN, V1, V2, Vn, right? So this you can call as some new vector, V1 prime, V2 prime, Vn prime. So the matrix serves as a way to map one vector into another in the same vector space. Similarly, I can think of another matrix B in the W space, such that it takes a vector W and maps it onto a different W prime. Okay. Now, here's the point. Suppose if I demand that these matrices, so the question is what kind of transformations will ensure this mapping V to V prime in the direct sum space? Okay. Now I want to ensure, suppose if this is my demand, that I want to ensure that the same matrices also do this mapping between V and V prime in the direct sum space. So how should my matrix, corresponding matrix in the V plus W space look like? Well, first of all, the matrices in the V plus W space, what are the dimensions of these matrices? How many rows and how many columns do they have? So they will have n plus m or n plus m times n plus m square matrices. Right? Why? Because matrices in the V plus W space are supposed to act on vectors that are n plus m dimensional, right? So suppose if you want a matrix to act on an n dimensional column vector, you need an n by n matrix. So suppose if you need a matrix to act on an n plus m dimensional vector, you need an n plus m times n plus m matrix. So this matrix has n plus m rows and n plus m columns. Does this make sense? Yes or no? Any questions about it?
I don't understand this part.
You didn't understand this part.
Sir.
Okay. So, see, what do my vectors in V plus W space look like? We just discussed the vectors in V plus W space are n plus m dimensional vectors. Right? If n equals 2 and m equals 3, the vectors in the direct sum space are 5-dimensional vectors. So the vectors in V plus W space, remember, vectors in the V plus W space are n plus m dimensional column matrices, right?
Yes, sir.
So let us say n equals 2 and m equals 3. Your vector basically is a given vector, which I can think of as a direct sum of V plus W, will have components alpha 1, alpha 2, alpha 3, alpha 4, and alpha 5, right? So what kind of a matrix can act on this to give me a new 5-dimensional vector? A 3-by-3 matrix cannot act on a 5-dimensional column vector. So I need a 5-by-5 matrix that acts on this. Right? So my also be 5-by-5 matrix, right? So matrices in the V plus W space have to be n plus m times n plus m square matrices. Is this point clear to everybody?
Yes, sir. Clear.
Okay. So the question is, I want to construct a matrix in this n plus m times n plus m as a n plus m times n plus m square matrix in this V plus W space, such that it preserves this mapping between V and V prime and W and W prime. In other words, I'm demanding that what is the class of matrices in the direct sum space which preserve this mapping. In other words, if I look at what is this V vector in the 5-dimensional space, I can write down V vector in the 5-dimensional space as V1, V2, 0, 0, 0. So suppose I can ask what is A in the 5-dimensional space. Well, that is very easy. You can simply write A11, A12, and then 0, 0, 0 along all the entries. That is also fine. See, remember that I can simply write down V in the 5-dimensional. Again, I will use the example n equals 2, m equals 3. This can be written as V1, V2, 0, 0, 0, right? So you would actually think that if A in the n equals 2 space is some square matrix A11, A12, A21, A22, then I can simply write A in this 5-dimensional space as A11, A12, 0, 0, 0, A21, A22, 0, 0, 0, 0, 0, 0, 0, 0. This is fun. this 5 by 5 matrix, right? This 5 by 5 matrix acting on this 5-dimensional column vector. What would this give me? A times V would simply now be A11 V1 plus A12 V2, then A21 V1 plus A22 V2, and then 0, 0, 0. So this is precisely your V1 prime, V2 prime, 0, 0, 0, right? So if I simply promote this A to a 5 by 5 matrix with a small block, the original 2 by 2 block, but with the zeros filled everywhere else, this guy makes sure that A acts on B to give me the exact same V prime, which I also got by acting in the original n equals 2 space. Does this make sense? Similarly, if I have in the m equals 3 space, for example, if I had a matrix B that took my W and gave me a BW, which was some W prime, then I can also make this into a 5 by 5 matrix. Okay, but the question is, suppose if I act, so what is the matrix I should act? What is the matrix I should act on the direct sum of these two vectors on V plus W such that both these original mappings are preserved? That seems like a complicated question, but it has an easy answer. So what am I asking? I'm asking that, look, if I simply act these on this vector separately, I can guess what the matrix is very easily. I will simply take the original matrices and then put in zeros everywhere else. Just as I constructed the vectors with zeros along the other directions, I will construct the matrices with zeros along the other components. Where, so for example, if this entry of the matrix is basically, what is this matrix? So this is, if I call this row E1, this is E1A F1, right? So if I simply say any component along F1 and F2 and F3 are 0, I'll simply write zeros everywhere else and I construct this matrix very simply. Well, that is easy enough, but what happens if you act this matrix? Suppose if you just take this A matrix and act on V plus W. Okay, suppose if I take this A matrix and act it on V plus W. What would I get? Well, it will preserve the mapping from V to V prime. I will get V1 prime, V2 prime. But since everything else is 0, I will still get 0, 0, 0. Right? Which means that the mapping W to BW is lost. Do you understand this?
Yes,
so
sir.
A is a 5 by 5 matrix, all right, and it does preserve the mapping between V and V prime, but it does not preserve the mapping between W and W prime. Similarly, you can verify yourself that if I construct a 5 by 5 B matrix and I act it on V plus W, it will preserve the mapping between W and W prime, right? So I can construct a 5 by 5 matrix such that it preserves the mapping between W and W prime, but it won't care anything about V. So the question is, I want to write down a matrix that preserves the mapping A and mapping B together. So the way I write this matrix down, there is only one choice that preserves both these mappings exactly as they were in the original case. And this matrix has to be constructed in a special way. And this way is called a block diagonal form. Suppose if I construct A plus B, which is the direct sum of these two matrices, as an A. So I'll go back to the n dimension and m dimension, and then we will take the example of 2 and 3 now. So this is an A n by n block, okay? And then this is a B m by m block, okay? Now this is supposed to act on an n plus m dimensional basis column vector, remember. So I'll write this down and then I'll erase it later. So what does this look like? This looks like V1, V2, Vn, W1, W2, Wn, right? So if my A plus B looks like this, now this n by n block will act on the first n components of this. But I should act it such that the rest of these guys don't act on the W, so I'll put in zeros everywhere else. Okay, so this is an n by m block of 0. Similarly, this B m by m block is going to act only on the W's, excuse me, as long as I have a 0 block here, m by n, that doesn't act on the V's at all. Does this make sense? So let us actually look at this in action, so it'll actually be easier to understand what's going on. So if I want to preserve both these mappings on the direct sum space, I should construct a direct sum of these two matrices A and B such that they are in a block diagonal form. So let us actually take the example of n equals 2 and m equals 3, and I will write this out explicitly. So n equals 2, the A matrix has the form A11, A12, A21, A22, and the B matrix has the form B11, B12, B13, B21, B22, B23, and B31, B32, B33. Okay, so what is the mappings that I'm talking about? In the n equals 2 space, the mapping is V goes to AV, which is basically A11 V1 plus A12 V2 and A21 V1 plus A22 V2. Okay. Similarly, W goes to BW, that mapping is basically B11 W1 plus B12 W2 plus B13 W3, B21 W1, B22 W2, B33 W3. Yeah. So I want to write down a matrix in the 5-dimensional space that preserves both these mappings. And the way I would write down, I allege to you, is A plus B is A11, A12, A21, A22, B11, B12, B13, B21, B22, B23, B31, B32, B33, 0, 0, 0, 0, 0, 0, a 3 by 2 block of zeros, and a 2 by 3 block of zeros. Okay, now you're guaranteed that if this matrix A plus B acts on the direct sum of V plus W, how does it act? You can easily guess that this 5 by 5 matrix, this is equal to A plus B acting on V1, V2, V3, W1, W2, W3, right? And this is equal to, so now you can easily guess that, for example, the A11, A12, A21, A22 is going to act on the V1, V2, excuse me, I wrote this as a 6. The 2 by 2 block is going to mix V1 and V2, and the 3 by 3 block is going to mix the W's into each other, and the zeros are going to ensure that the V's and the W's don't mix between themselves. Okay. If I had non-zero component, for example, if I had a non-zero component here, some alpha, right? Then this is going to, so here there is going to be a mixing between V1 and V1, V2 and some W2, right? As long as I only have zeros here, I can ensure that there is no mixing between the V's and the W's, and the original mapping is preserved. So this is going to be equal to V1 prime, V2 prime, W1 prime, W2 prime, W3 prime, exactly the same as before. Okay, so this is exactly my V1 prime, V2 prime, and this is exactly my W1 prime, W2 prime, W3 prime. Okay, so I hope you see how the block diagonal form of matrices is important in direct sum space. The direct sum space, if you construct the direct sum space as a addition, a direct sum of two linear vector spaces with the same or different dimensionality, then if you demand that the matrix in this you want to write down certain matrices in the 5-dimensional space that preserve this original structure of the mappings, then such a matrix in the 5-dimensional space should necessarily have a block diagonal form. I should also mention that not all matrices in this 5-dimensional space will have this form. Right? These are one class of matrices in this form. Of course, there are matrices in the 5-dimensional space that don't have zeros in this block and zeros in this block, right? So there are also matrices like that. That is not what I'm talking about. I'm not claiming that this is the only class of matrices, but the class of matrices that preserves the mapping in this direct sum space is one that has a very special form, and this form is a block diagonal form. Okay, so as a quick exercise, you can actually trivially verify. So let us actually write this down explicitly. So what this means is this, in symbolic notation, this is what it means. And you should get used to all these symbolisms, because it's useful to understand what's going on. But in terms of column vectors, it's very easy to understand what's going on. But sometimes, you can get lost in the symbols, but make sure that you understand what this means. So A plus B acting on B plus W is nothing but, I can understand this as AV and BW, right? The 2 by 2 matrix AV is basically V prime, and the 2 component column vector AV is basically V prime, and the 3 component column vector BW is basically W prime, right? So this is a 5-dimensional column vector. Okay. So the way I understand this column vector is basically I'm stacking the vector AV on top of the vector BW. So I can understand this as AV direct sum BW, right? So this is important. Okay. So in this way, the action of the direct sum of the matrices A plus B on the direct sum of the vectors V plus W can be understood as the direct sum of the vector AV plus the vector BW. Okay. And this is ensured, this equality is ensured because of the block diagonal form of A plus B. Okay. So you can actually quickly verify that the determinant of the composite matrix A plus B, what should it be? Since it is a block diagonal, the determinant of this matrix should simply be the determinant of the A matrix times the determinant of the B matrix. Otherwise, you can simply explicitly compute the determinant and verify this yourself, but this is simple enough to guess. And of course, the trace is trivial. Trace of A plus B would be basically trace of A plus trace of B. Okay, because they're block diagonal. So this is just trace of the 2 by 2 component is A11 plus A22, and the trace of the 3 by 3 component is B11 plus B22 plus B33. Okay. So how do I understand a matrix multiplication in this 5 by 5 matrix? Again, I will simply specialize to the block diagonal form. Suppose if I have 2 block diagonal forms with matrices A1 B1 and A2 B2. So suppose if I construct A1 plus B1 times A2 plus B2. Okay, again, you can verify this using the example provided. So just take 2 different 2 by 2 matrices and 2 different 3 by 3 matrices, and you verify yourself that this is basically equal to A1 A2 direct sum B1 B2. Okay, so these are some quick and easy properties that you can use in some practical measures. Okay, so okay, so I thought of finishing both direct sum and direct product today, but I had as usual, I have underestimated the time. So I will talk about direct products tomorrow, because that will take a little bit time. So I will stop here for now, and I will talk about direct product of 2 vector spaces tomorrow. And you would need both these concepts, surprising as it may seem, To understand what J equals L plus S is, you would need the concept of both direct sum and direct product. And direct sum, I'm hoping, is clear now because the U matrix itself is a block diagonal form, and this is where it comes from. You see, the fact that this J is a block diagonal form should not be any more of a surprise to you, because now the block diagonal form ensures that states with different J values don't mix. Okay, just like we demonstrated in this example, that if you have a block diagonal A plus B, the components V and the components W do not mix, right? The first block simply acts on the V's, the second block simply acts on the W's. Just like this, in this representation here, the first one by one block simply acts on the vector 0, 0, J equals 0, M equals 0. The second 2 by 2 block simply acts on the two vectors 1/2, and 1/2 minus 1/2. The third 3 by 3 block simply acts on the three vectors 1, 1, 1, 0, 1 minus 1, and so on and so forth. So none of this, because everything else here is 0, there is no mixing between, let us say, the 1, 0 state and 1/2 minus 1/2 state. Such a mixing is not possible. It's the form of this matrix guarantees that. Okay, so this is the advantage of the block diagonal form. Okay, so we will stop here for now, and we will continue tomorrow.